Okay, so today the focus of this lecture, let me see if I can zoom in here a little bit. Is on trusses. So a truss is a basic structure composed of slender members which are joined together at their endpoints. Joined together at their endpoints. All right, now you've seen these before. I know you probably, when they're building houses and you see a roof truss, will look something like this. Right. So you've probably seen something like this during the construction of a house or a building. It's a roof truss. You've also have seen these on bridges, you know. So this is one example. You might on bridges. A lot of times you'll see something that looks like this. Sorry, I didn't have it far enough for you to see it. So you see trusses that make up roofs. You see trusses that make up parts of a bridge, right? A truss is each term. Again, trusses are made up of these slender components here, and they're connected at the end. So these little triangles here is really a truss. So it's made up of these trusses, okay? And they're all connected at the ends. And as an engineer, you know, we are worried about, you know, what is going on here. As far as loads. What is going on there as far as a load? You know, what's going on here? What type of load are we seeing here? Okay. So we need to be able to analyze trusses. So we're going to be analyzing trusses. And for the most part, we're going to be using our equations of equilibrium to do this. Okay. So we're going to be using our equations of equilibrium to do this. And we know what those are. Some of the forces in the X, some of the forces on the Y, by the way, equals 0, sorry, equals 0, and some of the moments equals 0. That's it. Now, these members here, these slender members that you see, which make up the trusses, they're either in compression or tension. So in that sense, the members which make up the trusses are two force members. In other words, these members are either in tension or compression. So they're either in tension or compression. Okay. All right, so let me slow down here. I was going kind of quickly here. Our main focus is trusses. Here's the definition of a truss. Truss is a basic structure composed of slender members. These are the slender members, which are joined together at their endpoints. These are the endpoints, right? We worry about what's going on there. And they use on roofs, use on bridges. You'll see them on radio towers and cell phone towers, right? You go next time you go down interstate, you see a cell phone tower or something, because a lot of times they're pretty close to interstate. You will see them. You will see these triangular shapes, and you will see them on bridges. We need to be able to analyze trusses as far as the equilibrium equations are concerned. And we need to know how much the internal forces are. How much are each one of these members seeing as far as force? And then later on, when you take strength of materials, is your bridge or is your roof truss strong enough to support the loads? Or is it going to buckle, or is it going to shear, or what's going to happen? Something might happen to your roof, right? And they're two force. You're only going to have tension or compression in these members, either tension or compression. Okay. So again, a truss is a triangular element. Truss is a triangular element. All right, so let's do this. I'm going to start off with a very simple problem. And then I'm going to do a more complicated problem. And we're going to be spending quite a bit of time in this chapter. So this is not going to be the one that we rush through. Not that I've rushed into the others, but we're definitely going to take our time with this one. I'm going to work a problem, not from your textbook, from a different textbook. And here's the problem statement. It says, so this is a problem from a different text. All right, and here's the problem statement. Looking for it. This is a better pen. I hope y'all can see that okay.
Yes.
You can see it better, right? Determine the force in each member of the truss. And indicate whether the members are in tension or compression. So go ahead and draw. Let me get a pencil here to draw this. And then I'll darken it in. So our truss looks something like this. By the way, I graded the test while I'm drawing this. And I'm going to offer you an opportunity for some extra credit so you can improve your scores a little bit. We have like a rocker here. There's like one or two people I still have to grade their test. But for the most part, everyone did pretty well. But some grades could have been a little bit better. So I'm going to offer some extra credit opportunities.
Is there any way we could see what we got wrong on the test?
Yes. I really just, to be perfectly honest with you, I really just want to go over the test. I want to review every problem with, and I like to do that. I'd like to do that on Tuesday if possible, because that way you can see. I just want to work every problem.
That sounds great.
Because that way you can see, and some, I'm human. I make mistakes when I grade things, so maybe I didn't. That's really hard to see. That's a 45 degree. So I'm just going to work the test, but I'm waiting to get it from certain ones first here. Some people have not turned it in yet. All right, so we have some dimensions here. This is 2 meters. We have a dimension here.
Are those rollers on the bottom?
This is what they call a rocker. So it's not a roller. But you go back to the table, chapter 5, you will see how we handle a rocker. It's just one reaction force. Unlike a pin has 2 reaction forces. So this is point A right here. And this is point B. Oh, excuse me, this is not point B, it's point C. Let's see. Now, without knowing anything about statics at all, if you were to look at this, okay, all these 2 members are connected right here with this pin. Hold on, my internet's having a problem. Hang on. Can y'all hear me?
Yeah, I hear you. You're just going in and out.
And the pitch is getting blurry a little bit.
Yeah, it happens sometimes. It'll come up and says my internet is unstable.
I thought
So,
Okay.
so think about this. If you're pulling, here's two members, right? That make up, there's three members that make up the truss, right? 1, 2, 3. And let's say you're pulling here with this force right here. Think about this. One of these members, the fact that you're pulling here, one of these members is going to be in tension just by observation. And another one is going to be in compression. I don't know if you see that or not, but it's okay if you don't see it, because like I said, if you get the negative result, you know you assumed the wrong direction anyway. So what I'm going to do is isolate joint B. All these are called joints. That's where they're connected, okay? And if this is 45 degrees, this must be 45 degrees up here as well. But I don't know if you can see that. It's almost like by inspection, as you pull a load here on this point right there, what is happening to this member and what is happening to this? Okay. Well, you can see, or should be able to see, that when you pull here, you're actually pulling on this one. You're actually creating a tensile stress on this, or in tension. This one's going to try to prevent you from moving that way. So this one's in compression. One's in tension and one's in compression. But if you make the wrong assumption, your math will tell you. All right, so let me draw. What you're going to do now is you're going to isolate joint B first. Okay. And we're going to draw a free body diagram just of joint B. He said, Mr. Morris, why are you picking joint B first to isolate? Because I know more information about joint B than I do A and C. What I mean is, if I isolated A, I don't know anything. I don't have any forces down here to work with. I know I have some reaction forces that are going to come here later. I'm going to assume, I'll just make the assumption I got one here and one like this. I don't know if that's right yet. And then I got a reaction force over here. Okay, but I'm going to isolate this joint here first. Pardon?
Do we have the distance from A to C, or is that not known?
Oh, we do know it. Mr. Morris didn't put it down. Sorry. Thank you. Good catch.
Good.
All right, so it's 45 degrees here and 45 degrees up here. It's 1 square root of 2, right? So if we isolate, so step 1, we're going to isolate joint B first, because I know the most information, because we know the most information. In other words, we have a force there that we can actually look at. If we go down here, we're done. No forces. Same here, no forces. We start with B. So isolate joint B first because we know the most information. Next, we're going to draw free body diagram. Of the joint. Okay. So when I do that, Um, I'm gonna make a big dot there. That's my joint. I'm concerned about what's going on at the joint. So basically, I have a 500 Newton force. This is B. 500 Newton force pulling this way. So it's pulling here. So I'm going to assume this one's in tension. Now, put yourself at the joint. Pretend you're standing here, okay, at the joint, and you're pulling this way, and also I am saying from an assumption here, if I'm pulling this way, that this is going to be in tension. So it's going to want to pull away from the joint here. And I said this, so this one's in tension. It's pulling away. It's pulling on the joint. So it's in tension.
It
You
wouldn't,
have to put this up. Pardon?
it wouldn't be pulling with it.
Would the joint be pulling with it?
No,
Yes. What I'm saying is, when you pull this way, you're wanting to pull the joint this way, but this member is in tension, so it's pulling on the joint. You're thinking, well, the force should go this way. If the force, remember this rule. If the force is pushing on the joint, that's compression. That member is compression. If the member is pulling on the joint, that's in tension. One more time. The joint is what we're analyzing. If you are pulling on the joint, it's in tension. Okay, if you're pushing on the joint, it's in compression. So we're pulling on the joint. I'm assuming that this member here, which is member, I'm gonna call this F. I think I call it FBA. Yeah, FBA. I don't know what that force is, but I'm assuming it's in tension and that it's pulling on the joint. This one's pulling, and then I have another force this way that is pushing on the joint, because I'm assuming this member is in compression. So don't look at the member, look at the joint. Look at the joint. Pulling on the joint means tension. Pushing on the joint means compression. And this is going to be member FCB here, or BC, I guess we could call it. All right, so we know this angle right here. We know this angle right here. That angle is 45 degrees, right? Because that would be this angle right here, is 45. Questions about this? So we isolated the joint and we drew a free body diagram. We made assumptions. I'm assuming that this pin, the force this way is pulling on it. So I assume this is in tension, this is in compression. Now we have to use our equations of equilibrium. Okay. So basically, can't take moments here. There's no moments to worry about here with this problem. You know why? Because all of our forces intersect that joint. Where's your pivot point? So there's no moments to worry about. So I'm gonna put here no moments for this one. Actually, we won't worry about moments till we get into the method. By the way, I meant to tell you something here. I apologize, but this is called, this process that we're doing is called the method method of joints. Method of joints. And it's in your textbook. Look up method of joints and read through that if you get it free. And by the way, I posted like a 76-page PowerPoint that goes with this textbook that you can read through. But I find that I make better progress in class when I'm working problems rather than reading the PowerPoint slides to you. Okay, so that's why I like working problems. But I would encourage you to go and read through that PowerPoint sometime between now and next class. Just kind of read through the slides. It's 76 sheets long. I'd have put y'all to sleep. I'm going to sum the forces in the x direction here first equals 0. All we're going to be worried about is the sum of the forces in the x and the y because we don't have no moments. This is our equilibrium equations. I'm going to have 500. That's going to the right. This doesn't have a horizontal component, so we're not worried about FBA. Now, we want, obviously, this component here, right? We want that component of FBC. We don't need the vertical component, we just need the horizontal component. So you can do this two ways. This is your, you could say FBC sine of 45, because this is the sine from this angle. It's the sine of 45. Or you can also say cosine in this case. But be careful with that because that doesn't always apply. If it was a different angle other than 45, it's not going to work. This is really the sine of 45. To get this side here, because your angle's here. Your angle's not down here like it usually is. Usually we're working with this angle here, the horizontal. This one's angle opposite. So, you know, it's the sine of that angle. So we got 500, and then we have this component here, which is going to be minus FBC sine 45 degrees, because that's the component. That's the horizontal component, FBC equals 0. When you solve for this, you're going to get FBC equals, I got 707.1 newtons. And then you do this, put parentheses, compression, okay? Put compression there. Why am I doing this? Because this member here is a compressive force on the joint. Okay, one more time. Equation of equilibrium, sum of the forces in X. We got 500 going to the right. Then we have to take the FBC minus FBC sine of 45. And every problem we've done up to this point has always been cosine to get the horizontal. But that's because we've always used this angle here normally. And you could do that here too, because the angle is the same. But, and get the same answer. But you wouldn't, if you had different angles, you wouldn't, if the guess was 30 and 60, that ain't gonna work. You would have to use, like for example, the sine of 30 and or the cosine of 60. Do you see what I'm saying? Or have I confused y'all? Please ask questions.
So you would take the 500 to the other side. So you would subtract it from both sides and then divide everything by
Sine 45.
sine 45.
Yeah, I just took the, divide. If you take 500 over the other side, it comes negative 500. And divide by the negative of sine 45, you should get 707.1 newtons. Is that what you got?
Yep. That's
Somebody check my map.
doing it wrong. I had it in radians, I think.
Yeah, if you have it in radians, that's going to cause you to have a migraine. I have a little bit of a headache today.
All right, that makes sense.
All right. So the only thing we did different here, okay, we isolated this joint and we put the equations, we used the equations of equilibrium. And we had to assume, you know, whether it was in tension or compression based on inspection. But what was different here, you guys in this class and myself, we've always would take whatever FBC is cosine of this angle, right? And you could have here, you got 45. But let's say it was a 30, let's say this was a 30-degree angle, this was 60. So you would do FBC sine 30, or you would do FBC cosine 60. You see what I'm saying? Either one would be okay. So now I'm really confused. I'm gonna go ahead and do some of the forces in the Y. We got a minus FBA going down plus FBC. Now watch this, cosine 45 degrees, because it's this angle here. So what this force cosine of the angle is going to give me
Plus 500.
I'm sorry?
He said plus 500?
That would be the result of this. Yeah, because 500, you're not talking about this force, are you, Tim? You're talking about the result for these two, right? Because if you plug this number in here and set that equal to 0, you're going to get FBA equals 500 newtons in tension.
Oh, I thought you were doing what's FBA equal to?
This FBA here is this force coming down here, right? That's a vertical force, see, because we're doing it in the Y direction. See, this is the Y direction and this is the X direction. So this is a negative FBA because it's pointing down, plus this force here, the vertical leg of this is going up. So it's going to FBC cosine 45 is going up. We know what FBC is. You plug that in and you can take the FBA over to the other side. So what is 707.1 cosine 45?
Or 99.9.
You say 499.9?
Yep.
Yeah, so I just round up to 500. All right, so now let's see now. So we can do one of two things. I'm going to go and analyze this joint next here. Okay, I'm going to go analyze this joint because I know the force in this link now. What is that force? It's a compressive force. Okay, this is where I'm going to probably lose you. I hope I don't lose you, but I'm probably going to if I'm not careful here. We have to go and analyze. This might be the only problem that I work today too. We need to analyze this joint next, okay? I'm going to draw the free body diagram now. So step 4 here is I'm going to draw. By the way, this is the abbreviation for free body diagram. Draw a free body diagram. Point C. Okay, so let's draw that. Okay, here's that point C right there. Notice my reaction force right here. Where did I get that from? Did I just pull that out of the air?
No.
I got that from the, it's a rocker, right? And I got that from that table. So I got a reaction force right there that does this, right? It's pushing up like this. And this is going to be point C. Now, this is where I'm hoping I don't lose you. I said this member right here, the diagonal member, all right, I said that was pushing on B. It's a compressive force. It's pushing on B. What is happening at this point, that same link here or element? Are we pushing on C or pulling on C? Be careful.
On C.
Are we pushing on C or pulling?
You're pulling, right?
But if I did,
I mean, yeah, it's very hard to see sometimes. Even something like this. It looks simple, but this link is in compression. So you're pushing on B. If you're pushing on B, okay, think about this. Think about if someone was standing at B and someone was standing at C, and you know, if you're pushing this way, I know I'm gonna lose y'all. I know. All right, let me try to rethink this. All right, so this diagonal here, we said is in compression. You're pushing on it. When something's in compression, it's being pushed on. But we're actually pushing on the joint. So this same member is also going to be pushing on this joint. It's going to be pushing on this joint as well. You see that?
Mm-hmm.
Okay.
Yeah, that makes sense.
Sometimes people have a hard time seeing it. So we're pushing on this joint here. So we have our reaction force here. We know that from the table, right? It's a rocker. And then we know that this is pushing on that joint right there. So we're going to call it, we know this is FBC. We know, we already know what that force is equal to. It's equal to 707.1 newtons. Okay. Now my reaction this way, I'm going to assume, okay, and here's my assumption. So if I'm pulling this way here, I'm just going to assume I got a reaction this and this link here.
Pulling.
I'm just going to assume.
Tension.
I'm going to assume it's going this way. Pulling. Now, if you're wrong, you'll get the negative result. It will tell you. So in other words, if I solve for this and I get a positive result, then I know I'm going the right direction. But if I solve for this and I get a negative result, I now know that I went the wrong direction. So let me work now. So let me do this. We got to do the equations of equilibrium here for this. Now this angle right here is still 45. That angle is 45 degrees right there. And this is going to be F, we're going to call this FAC here. I don't know what that is. I'm going to try to solve for FAC first. So again, our equations, I'm going to abbreviate this if okay with you guys. Equations of equilibrium. Okay, I'll write it out. Equations of equilibrium. Let's sum the four, no moments here. That comes later actually. Sum of the forces in the X direction. This really, what we're doing now is really not new. We've been adding forces in the X and Y direction all along, but now we're just doing it to analyze the joints of this truss. Okay. So we have negative FAC because we're going to the left. So it's negative FAC plus, see? Now, what is the horizontal component of this? It's going to be FBC cosine of 45 degrees equals 0. Well, I know what FBC is. So somebody solve what FAC is equal to.
$500, right?
Yep. Did I get a positive number or did I get a negative number?
Positive.
Okay, so my assumption here is correct. Positive number means I'm good here with my arrow. And it's going to be newtons. And am I pulling on the joint or pushing on the joint? FAC.
Pulling.
So it's tension. Okay. Don't worry, I'm gonna go back and review this. I'm gonna work this problem, go back and review it, then I'm gonna let y'all go get your test together. I'm gonna work the other test. I'm hoping Tuesday. Sum of the forces in the Y direction equals 0. What do we have? Well, we have, I'm gonna call this, if you don't mind, I'm gonna call this CY going up. That's the reaction force, CY minus FBC sine 45, because now we want the vertical component, sine 45 degrees equals 0. So this is CY minus, again, 707.1 newtons, sine 45 degrees. CY equals what?
500.
500. A lot of 500s here today, huh?
Yep.
Okay. All right. So the last joint A, is pretty easy actually, because now you can. Don't worry, I'm gonna review this whole problem one more time. I don't care if this is the only problem we do today.
We can
I'm
have
gonna
that.
make sure if you go back to the original problem, we have this horizontal force here, right? We just found what CY is right here. We just found that. So tell me by inspection, we just found that this is equal to 500 newtons. by inspection. What would AY equal?
500.
500, right?
Yep.
And what would AX equal? I'm going to work it for you. I'm going to work it. I just ask you right now to by inspection. What would AX equal?
250.
500. We only have two forces, 500 here vertical and 500 there. Let me work it, okay?
Angle.
This is what the free body diagram looks like, okay? Going back to the original free body diagram. You don't have to go back to the original.
It's the same on each side because of the angle though, right? Because it's a 45, 45. If there was
Well, I mean,
angles,
well,
be
hang on.
numbers.
Hang on just for a second. Hang on. So this is what was given to us, right?
Yeah.
Okay, and then we didn't know this one yet, right? We just found that. That's equal to what? 500. You solved it. Now we have, watch, we have a pin joint over here. Pin joint, right? And I said, I'm assuming, I don't know for a fact yet. I'm assuming here. So if I sum, sorry, if I sum the forces in the y direction, tell me what I have here from the diagram.
1,000.
It'd be 500.
Well, okay, we have, okay, so you want to take that 500 right there, okay?
Yeah. And then FBC going
just-
the Y direction would be sine.
Hang on now. No, all we're not worried about no angles now. All we're doing is sum of the forces in the y direction. We only have two of them.
Okay.
Bye.
So
So watch what happens. I want to show you. This is very important. What I'm going to show you here. I'm running out of ink with my red pen. Sorry.
AY.
Equals 0. Now watch. Watch this very carefully. I don't want you to miss this. Don't blink your eye.
Oh, negative 500.
AY is equal to negative 500 newtons.
because it should be pointing
What's
down.
wrong with my, pardon? Got to
It
point
should-
down, doesn't it?
Yeah.
Got to point down. So this is what I really should have right here. That should be AY. Now think about that for a minute. Does it make sense? If you're pulling here, isn't this one to pull back?
Yeah.
If you're pulling right here with this force, this is going to want to pull back so you don't rip it out of the floor.
Yeah.
You see that? And this member's in tension. This member's in tension as you pull here, and this is pulling back. This member's in compression. All right, let's do the sum of the forces and the X. I'm gonna have what? AX. Look, my initial assumptions are wrong. AX plus 500 equals 0. Well, look, I got AX equals negative 500. Guess what?
Because it should be going to the left.
It should be going this way. AX should be going this way. So you see, I got the right magnitude, right? I got the right magnitude, the right size out of the wrong direction. Let's review this problem. And then I'm going to call it a day. I'm going to go get your test. You will see your test within 15 to 20 minutes. Okay?
No.
This is test chapter 5.
I have one quick question.
Okay?
See why he wants to know if that's tension?
Or compression.
Compression, right?
Is what in compression?
CY,
CY.
because it's pushing, so it should be compression, right?
Well, this is just a reaction force, but it is
Okay.
pushing on just, yeah, worry about the joint itself. But we also found the internal forces, which I want to talk to you about later, but we actually found the internal forces in these members here.
Okay, so the reaction, we don't have to say whether or not it's tension or compression. Like,
Yeah,
we,
not with your reaction force. No.
okay. Yeah, that was just,
That's a very good question. All right, so let's review this problem. Okay, let's take it from the top. You've already written it down. Now you can just focus on what you've written down. Right? The problem statement says, determine the force in each member of the truss shown and indicate whether the members are in tension or compression. So I drew exactly what the book had. I drew the diagram. Okay. And I picked joint B first. Why did I pick joint B first?
Because you
could've
knew
picked
the
any
most
joint, but
information.
I had the most information. What was my information?
You had the magnitude and direction of the force.
Very good. You have the magnitude and direction of the force 500. So what I did is I isolated that joint and I drew a free body diagram of it. Okay. So I came down here. Here's point B. There's my 500 newtons pointing that way. I'm assuming here that when you pull this, I'm looking just by inspection, I'm looking at this. It looks like you're going to pull on this, putting this member in tension, and then you're going to push on this one, putting this member in compression. So what it is so in tension, you are pulling on the joint, and compression, you are pushing on the joint. So we got this free body diagram. Then we have to use our equations of equilibrium. And we got it right. I mean, our assumption was right here because we didn't get a negative result. We summed the forces in X. We got 500 going to the right minus FBC sine 45. You could have done cosine 45 if you use this angle here, okay? This could have been 30, 60. If that was the case, you could have said cosine 60 or sine 30. You understand what I'm saying when I say that? I'm talking about this angle right here. Right now it's 45. Cosine and sine of 45 degrees is the same. But this could have just as easily had been a 30, 60, 90 degree triangle. So we sum the four. We got 500 minus FBC sine 45. I want to make sure you understand how I got that. Does everybody see how I got FBC sine 45?
Yeah, I see it.
Okay. And we solve for FBC. Now FBC, we got a positive number there. We got a positive result. Hang on. I don't know what just happened. We got a positive result there. So that means our assumption that I put in compression is correct. FBC is correct. It's in compression. Then we did sum of the forces in the Y minus FBA plus FBC cosine 45. That's the vertical component equals 0. FBA is equal to 500 newtons in tension. Okay, I assumed tension. And when I got a positive result, it confirmed my result. When I got a plus. If I got a negative here, that would indicate that direction was wrong. But I got a positive result. So that's right. And then we did the free, so then we went next to C. We knew the most information about C next. Because we just calculated what this force was in this linkage here. We calculated this right here. And so we had one force and we had two unknowns. So we draw a free body diagram. If B is in compression, right here, if B is in compression, so is C. C is in compression. You're pushing on it. So here comes the force right here of 707.1 newtons compressing joint C. The other one, CY, we know is a reaction force due to the rocker. And I assume this one, this red one here, I assumed it. And then we sum the forces. Our equations of equilibrium here. Hang on. Okay. And minus FAC, look, minus FAC going to the left, plus FBC here. This one, the horizontal component of this is going to go to the right. Cosine 45. You solve for this, guess what? We got a positive number. Our assumption's correct. If we'd have got a negative number here, then we'd have had to change this arrow going to the right. This is it. This member's in tension. This member's in tension. Then we sum the forces in the y direction, and we were able to find our reaction force. Then I went back to the original 3-by diagram here for a minute because we were given this one. We knew this was a rocker here. We knew that was a rocker right there. We didn't know what the force was until we went through this analysis. But now we know this is 500 also. Okay, so the only two unknowns we had now is AY and AX. You only have two forces in the X. You only have two forces in the Y. So what we did here, $500, right? 500 to the right plus AY. Oh, I'm sorry. Wrong number. This one. 500 up. 500 up plus this AY going up. The red one's the initial one, right? The red one is the initial one I had. It's the wrong assumption because I got a negative result. So I had to change it around. Same thing here. Sum of the forces in X, AX plus 500. So 500 this way. And then this is my initial one, right? My red's my initial one. So I'm getting confused here with these. I drew these after the fact, but these are my initial ones. So I got AX plus, so I get a negative. So I have to go. So these are the correct, those are the correct directions there. All right, so we're going to work another problem like this next class. I was talking to a student, I'm not going to mention any names, about the possibility of having some help sessions. And I'll be able to do more of this after the 30th. But I'm not going to, I want to encourage you to reach out to your classmates and discuss these things that you're having trouble with. You know, you can share your emails if you want. You don't have to. You can work by yourself. No one's forcing you to work with anybody. But you can work with others to kind of help understand these problems better. So I've got your test graded. Some were not, you know, some were not your best. So I'm going to work the test. But in order for me to work the test, I got to wait till, oh, I don't want to work it. And then someone can turn their test in and get 100. So I'd rather wait till I get all the tests. I'm going to work the test. And then, in fact, I'm going to work all the tests going forward. We got this test and one more test, I think, in the final, I think. No, we just have the final, right? Don't we just have the final after this one? We have one more test and then the final. Is that right?
Yep.
Yes.
Okay. So this test I'm getting ready to give you is your third test. And then the final. So I'm going to work the test you just turned in, And I'm gonna work this one too, the one I'm giving out today, and when I get it back, I'm gonna take a whole class period and work through it. I really believe that's the only way you can truly learn what you did wrong. But Mr. Morris is not here to hurt anyone. Okay, I'm not the type of teacher who wants to go failing people. But you have to meet me halfway somewhere. So put forth your best effort. I told you the story about Mr. Morris making A's in the bachelor's degree program, right? And I got the same teacher for my master's degree. First class I ever taken in master's degree program. I got a 40 on my first test. And I had this teacher the whole time just about in the bachelor's. He wrote on the test, "This is not the bachelor's degree. This is the master's degree." So that was a wake-up call for me. But I'm not here to hurt you. I'm here to help you learn. That's the main objective here, is for you to learn. I don't care about grades. I know you care about grades because it's going to reflect in your GPA. But I'm more concerned about you learning. The grades are good. I don't think anyone has less than a B in the class right now. Unless, of course, you haven't turned in anything at all, then that might be a different story. But you have to turn, it's kind of hard to pass something if you don't turn anything in. I'm going to stop the recording here.